Okay, so welcome to this course. So this course is on quantum Gaussian states. So this is I hope all of you know what is a normal distribution on the real line. Okay, so if you have done any continuous probability, course on any continuous probability, you must be knowing what is normal distribution. So if you, then there is multivariate normal distribution, which is defined on Rn. So how do you define multivariate? There are many ways of so a normal distribution is determined by its mean and covariance and variance, right? So a multivariate normal distribution is also determined by a mean, which is a vector. And if it is a Rn, if it's a if you can define the Gaussian measure on Rn or any n-dimensional vector space, then you have a vector which is the mean, and you have a covariance matrix corresponding to that. So you can extend this to a Hilbert space. I mean, for infinite dimensional, there is a difference whether you extend it to a Hilbert space or Banach space or some other. There are other topological space or something. It depends on that whether you put a topology or not. Depending upon that, there are restrictions. You can't always have a Gaussian measure on infinite dimensional Hilbert space. For example, a normal Gaussian is not available in Hilbert space. Normal Gaussian means with mean 0 and variance 1. For example, so you need a covariance operator. The covariance operator cannot be identity in infinite Hilbert space because there will be a trace class condition. So it has to be a trace class operator in a Hilbert space. So infinite dimensional is not. So we will not be dealing with infinite dimensional Gaussian distribution, even in the non-commutative case, whatever the quantum thing. We will be dealing a quantum analog of the finite dimensional Gaussian distribution. Okay, so that's what. So there will be a covariance matrix, and all that we will be defining. Okay, so the prerequisite of the course is almost covered in the last course, the previous course on quantum probability. But I will state the theorem in full form in whenever it's required. And either you can go and look at the corresponding video there. The video is available in the playlist. Either you can do that, or you can read it somewhere else, or you can just assume that and continue with this. If you are not interested in the mathematical detail, you can assume that theorem, just understand the theorem. You need not go through the proof and continue with this. You can do any one of these things. Okay. So the next thing I want to show you is so the Gaussian state can be defined, I think, in many ways in the quantum setup. Okay, there are many ways like quantum group. You can use quantum group. You can do many things. We are going to, in this course, for us, the Gaussian state is in a very restricted meaning. We are going to talk about what is called a bosonic Gaussian state. Gaussian state on a boson Fock space or symmetric Fock space. Okay, which we have already discussed. So, like a multivariate Gaussian state is defined. How do you define a multivariate Gaussian state? You take the coordinate projection. Each coordinate projection, if you have a measure on Rn, when you take the coordinate projection has to follow normal distribution. That's how you define the Gaussian. That's how you define the Gaussian on Rn. So similarly, here we have some called position operator, momentum operator. So if they are some self-adjoint operators, if they follow Gaussian, whatever the sense we are going to define, then it's called Gaussian. That's what we do. Okay. So, yesterday in Arun's lecture itself, in the notation is fixed. We will be using the bracket notation, and for us, always we will have H is a Hilbert space, and mostly our Hilbert space will look like Rn and L2 of Rn. Okay, this is all those functions from Rn to complex numbers. Okay. What should I do? It is hiding there. Yeah, I didn't check. Varma and the better. Okay, no problem. So all those functions such that integral mod f, which with respect to Lebesgue measure, integral mod f square is less than infinity. Okay, all square integrable function defined on Rn, complex variable function which are square integrable. Okay, on Rn with respect to Lebesgue measure, the usual measure. Okay, dx, let's say. Okay, so this is what this is our L2 of Rn. We will identify this L2 of Rn with the Fock space, which I will be defining. So the gamma of Cn, the Fock space of n-dimensional vector space. And we will define Gaussian state on this. But before that, let us just restrict to a general Hilbert space. So we will be using, this is H is a Hilbert space. Okay, this is a Hilbert space. And with respect to L2 of Rn, you know that the inner product, if you have two function f and g, then the inner product is given by f bar g integral over Rn with respect to the Lebesgue measure. And our inner product is, as in the earlier course, as in any other quantum course, our inner product are conjugate linear in the first variable and linear in the second variable. Let me not write all those things. And by already know what is a ket vector, all that. Okay.
It's okay if you don't say.
No, it's okay. Let me say that. So if you have a Hilbert space, any element of the Hilbert space will be denoted by a ket vector. See. So what is a Hilbert space is just an infinite. Our Hilbert spaces are infinite dimensional. Okay. So H is some infinite dimensional inner product space. Okay. So you should know what an inner product is, of course. So our inner product is linear in the first variable. Sorry, linear in the second variable. Usually inner product is linear in the first variable in mathematics, but here it's linear in the second variable. And conjugate linear in the first variable. Okay. And any vector in the Hilbert space is denoted, it's denoted like this. Any vector, xi vector is denoted like this. And any vector, so for a Hilbert space, its dual is itself. Okay. The all continuous linear functional, all bounded linear functional. You have done a course in functional analysis, some basic course. But that will be needed. That will be too much. So you should know at least the basic of. So if you have any linear functional, because it's going to be infinite dimensional, it's not finite dimensional. So you will need basic functional analysis. Okay. So any linear functional on this H will be given by eta. It's given by a vector in H itself, and it's evaluated through the inner product. So by eta, by an eta in H star, okay, which is actually identified with H through the following, which is just a linear. This is all those linear functional from H to C. Okay, phi is bounded, whatever it means. Okay. So for any linear functional is given by this. So eta, this is eta acting on any xi, a vector, is just the inner product. Okay. So this is the convenience of this notation. That's why this bracket notation is used. Okay. So this is, so any, if you can just evaluate the inner product, and that is what how the linear function will look like. At the same time, this is, that this is an operator. This is a rank 1 operator. Okay. This is in what is called B of H, all bounded operators. Okay. These are all notations we have already fixed, which I am just recalling. B of H is all bounded operators on H. Okay. And this is what is a rank 1 operator. So if this is an operator, this eta acting on any other xi prime. I'm also not used to this notation, bracket and all those things. I use functional analysis. I use usual just xi or something. So I'm getting very confused. So this is just going to be, you take the inner product out. So you just evaluate the whole thing, just put it together, and you get this eta xi prime, which is the inner product, which is a complex number. So you can take it to this side. So which is just eta xi prime. And then this is a constant, this scalar times this vector. Okay. This is the rank 1 operator. So this is the bracket notation we will use. Okay. So hopefully I will not get confused. So that's about the bracket notation. So there is something called state, which we have already defined state, but here for us, it's very restricted. For the earlier course, for us, the state was something you have an algebra and you have a linear functional, positive linear functional with some condition, phi of 1 is 1. But here we will just define it like this. For us, a state on H, this our H is the state space, okay, on H. So H is the whatever, the H is a Hilbert space we have, and a state on H is a positive trace class operator. Operator row with trace row equal to 1. Okay. So maybe I will recall what is positive. Arun, if you have, I mean, later or somewhere, if you have any mathematics, something which I have to go through, I can go through.
Yeah.
I mean, maybe not the proof, but certainly, we need not finish the whole thing. I mean, it's better that we go slowly and.
Previous class, you had said that state is essentially linear functional with.
So earlier class for us, state is something when in the finite dimensional case, it is just an algebra.
Yeah.
And you have a linear functional from the algebra to complex number, but it is positive linear function in the sense that it will take any positive element, A star A should be a positive number, and phi of 1 should be 1.
So here you not use the same.
We can use it, but here everything is given by a trace class operator.
Okay.
So better we use that. Okay, that's all. So in general, we will use what is called, this is for a finite dimensional case. In the infinite dimensional case, usually a quantum probability space, there are different versions, but the most accepted version is M is what is called a phenomenon algebra. Okay, which is some special kind of algebra. So there you have a state, and the state should be continuous. This is infinite dimensional. So it should be continuous under what is called sigma weak topology on that. Okay, but then here the algebra is here, but see the explanation is the following. Here the algebra we have is H. Maybe thank you. So here the algebra I identify our algebra to be B of H. Okay, then the sigma weak topology is what is given, what is called B of H is a dual space. It is dual of something. It is a dual of all trace class operators. Okay, so which we approve in the graduate analysis course. So any linear functional which is sigma weak continuous, that is continuous with respect to weak star topology, is actually given by a trace class operator. So that is why we are using trace class operator, and any linear functional on B of H which is continuous in the right topology, weak star topology we want to talk about, which is actually given by so if you have a phi from B of H to C, that is actually phi of T is actually given by trace of rho T for some rho. So that is why we are using that definition itself. We don't want to confuse ourselves with all this weak star topology and all that. Okay, you can forget about all these things. Okay, for us a state is just it is just consistent with our earlier definition, but then we are just using we are just calling a trace class operator, or it's called a density operator. Okay, it's also called as a density operator. Density operator means it's positive and trace is 1. Okay.
But this is same as considering as a functional operator.
Yeah, that's what I'm saying. You have an operator. The functional is basically T going to trace rho T. That's all. This is the function.
Okay.
That's
so
all.
it is using this.
Exactly. So we are just using this. If you're using functional, if you want to define the same way as, that gives the more clarity. If you have understood the functional, then that is, if you want to use, that's the right definition. Okay. This is you derive this. Every linear function is given by this. We derive this. Okay.
This is the non-competitive analog of the Rees representation.
No, what is which Rees representation there on the Rees the continuous functional?
Yeah, every function you have a continuous. For a continuous functional, you can define a probability mass function so that you are integrating with respect to that. So this is just a
correct. It's in a sense, yes. Yeah, in a sense, yes.
Not
exactly. No, it's not exactly. It is the analog of what is called L infinity. The pre-dual of L infinity is L1. The pre-dual of L infinity, the L infinity function, which is, see here what we are using is B of H cannot be identified with continuous function. We have to identify with measurable functions. Okay, B of all measurable functions or something. The commutative analog is measurable function. When you have, of course, in the finite dimensional, everything is same. In infinite dimensional, we have to identify with the L infinity function. So L infinity function corresponds to B of H, and this trace class operator corresponds to L1. Okay, so B of H's dual is very big. B of H is not separable. It's a huge algebra. Okay, it's not separable, another thing. So the pre-dual, the dual of this trace class operator is B of H. Okay, so this pre-dual is given by L1. So that is the analog we are using.
Okay.
So the continuous function will correspond to what is called C star algebra, not Feynman algebra. Okay, here what we are using is we are not going to use all those analog Feynman algebra, all those terms we are not going to use in this course. But the B of H, we are considering as a phenomenon algebra rather than a C-star algebra. C-star algebra has only norm. The phenomenon algebra means you have to put other topology, strong topology, and we can't work with just norm topology. Okay. Here, actually, when I say this continuous with respect, this row is continuous, it is continuous with respect to what is called a weak star topology, given by the trace class operators. Okay, but anyway, we can forget about all these things. For us, the state is just a trace class operator with trace row equal to 1. I hope let me just recall what a positivity means. Positive means this. I mean, for the time being, I write xi, I don't write ket and all that. Okay. Whenever it's needed, I will use especially when I use rank 1 operator and all those things, I will use that. Okay. This is greater than or equal to 0 for all xi in H. Okay. This is positivity. And trace I have defined already. Trace of any operator T, where T is greater than or equal to 0, a positive operator. Or when the trace exists, you can use the same definition. Okay. But positive operator you can define because trace can take the value infinity. Also, it can be infinity. When it is finite, we say it's a trace class operator. Okay, trace T equal to summation EI T EI, where EI equal to 1 to infinity, and this EI is an orthonormal basis. Okay, is an orthonormal basis. Okay. So this is the definition of state. Okay, so the next one we want to define is random variable. What is called a random variable? Okay. For us, a random variable is just a self-adjoint operator, unbounded self-adjoint. It will need not be bounded. Okay, the definition. Okay. So, a random variable. I mean, for us, the quantum probabilities. So let me remark a few things. So we have a density operator. So say in Arun's class, you could have seen that a vector in the Hilbert space is also a state. Okay, that is, you can consider the rank 1 operator corresponding to that. Okay, so if this is you can call that xi in H is also is called a pure state. Okay, I mean, if you have a xi, called a pure state, and this corresponds to this density operator. Okay, we should have something more. This xi, norm of xi should be equal to 1. Okay. So this is just a rank 1 projection onto the one-dimensional subspace generated by this xi. Okay. So this is the pure state, and the definition coincides. Okay. So this is about the state. Then we want to define what is called a random variable. Okay, a random variable for us is just possibly mostly unbounded. Okay, mostly unbounded self-adjoint operator on H. So here I should remark a few things. What is an unbounded operator? An unbounded operator mostly will not be defined on all of H, especially when we have this. We say it is on H because we want to have the domain which is dense in H. So we have to see when we define adjoint of an unbounded operator, it is with reference to the H. So we have to say that it's an unbounded operator on H. That's important. Okay? Since we are going to talk about adjoint and other things. So that is done with respect to H. Okay. So by this we mean random variable X is an unbounded self-adjoint operator X on H. So we have the domain of X, which is contained in H, is dense. Okay, it can be bounded also. By this we include bounded case also. Okay, mostly it will be unbounded. Our operators are unbounded operators. Domain of X contained is dense, and this is a self-adjoint operator. So for this we mean that it should satisfy this relation. Xi X eta should be equal to X xi eta. For all vectors, this is defined only for vectors in domain of X. And this is not the definition of self-adjointness. This is the definition of what is called symmetry. This just means, I mean, we have defined all this in X star, the adjoint and all those things. This will just means that X is contained in X star, whatever means. X is contained means the graph of X will contain in graph of X star. Actually, we will not need all these details when we work with Gaussian states, because we will not be knowing that we don't know. I mean, we don't know means the community, mathematical community, we don't know what is the domain of position operator and momentum operator in detail. I mean, we know it, we know abstractly. We can't, when we work with this, we will work with a subspace of the domain. We will not work with the whole domain. Okay, because it's not clear, it's not able, we are not able to say that whether some vector is there or not. We will be mostly able to say whether some vector is there or not. But it is not clear. I mean, there is no description of all the vectors. There is a description in terms of limits and other things where the derivative exists and all that. Okay. But what I want to say is there is no workable domain, where workable subspace, which we want to, we can identify with that. Okay. So there are some conjectures, but it's not proven. Okay. So, but self-adjoint is something more. That just means that this domain of X star, however we define this, that is also equal to domain of X. That's what it means. Okay. This definition implies that X is contained in X star. Further, the domain of X star is equal to domain of X. That is what it means by, then it is X equal to X star. Okay. We will not deal with, I mean, we will not have occasion to talk about what is X star and all those things. So I will not recall those things. Okay. So I'm not, by some reflex I touched it. Sorry. Okay, so this is the self-adjoint unbounded operator. And the spectral theorem says the following. Okay. The spectral theorem is just to define the probabilities. The nice thing about the probability, the subject probability is, whenever you want to discuss probability measures, it's enough to discuss its characteristic functions. Okay. So, which is just a Fourier transform of the measure. Okay, it's equivalent to work with the characteristic function. Mostly that's what we will do here. So we will not be working with the actual distribution of a quantum. Quantum state is, that's a quantum state. But if you have a random variable, that will give a classical probability distribution. Okay. So that classical, we will only be working with its characteristic function, not with the actual distribution. Okay. So whatever I'm doing is actually, this is just to understand what is happening. We will not be really working with these things. Okay, spectral theorem and all this, whatever the distribution I'm talking about. So you need not worry about it. Okay. So the spectral theorem, which we proved actually in somehow, spectral theorem says the following. Okay. So X is a self-adjoint operator. Then there exists a spectral measure P, so which is Borel sigma algebra of real line. Okay, this is a sigma algebra of sets on real line. Two projections on H. Okay, this is all projections. Okay, it is a projection valued measures. Okay, projections on Hilbert space. So okay, let me recall what it is. P of the whole of R should be equal to 1, the identity operator, and P of the empty set should be 0, and P of E1 disjoint union E2. This is my notation for disjoint union. E1 union E2 should be equal to P of E1 plus P of E2. Okay, and P of some countable union n equal to 1 to infinity En should be equal to summation P of En, n equal to 1 to infinity, and this summation is an infinite sum. So you have to specify the topology in which it converges. So this is what is called a strong topology. By this, I mean the following. You evaluate a vector xi on this. Maybe I will write it in the next line. This just means P of this n equal to 1 to infinity En acting on any vector xi is equal to limit. This is a finite sum, which makes sense. N equal to 1 to n goes to infinity. Okay, P of En acting, this whole thing acting on xi. Okay. This is a finite sum, and the limit, this is what is called a strong convergence. Point-wise convergence is what is called strong convergence. Okay. An operator Tn converges. This is the definition of strong convergence. Tn converges to T strongly if Tn xi converges to T xi. Norm convergence means norm of Tn minus T should go to 0. Okay. I mean, on behalf of bounded operators, there are many topologies. The usual topology is the norm topology. Norm convergence means norm of, we will be always using the strong convergence, because the reason is there is underlying phenomenal algebra and other things. Okay. So this is what, if Tn minus T go to 0, this is what is called norm convergence. Okay. Here we will not be talking about this. We will be talking about the strong convergence. That is Tn minus T goes to 0 means that is, I mean, that is the operator norm. Tn xi goes to T xi for all xi in H. Okay. This is what is called strong convergence. Okay. So this limit is in the strong topology. That's how the summation is in the strong topology. So this is just a measure. Measure is just a countably additive set function defined on the sigma algebra, Borel sigma algebra. Here we have a set function which takes values in the projection rather than real line numbers. I mean, rather than real numbers or complex numbers. If something takes values in positive real line, that's called the actual. That is what usually called as a measure. It can take value in complex number. That is called complex measures. It can take values in projections in a Hilbert space. Wherever you can add these things and make sense of countable sum, you can have a measure on that. Okay. So this is what is called the projection valued measure. So you have a projection valued measure, and then this X is the self-adjoint operator. Then X is actually given, the spectral theorem says X is actually given by this small x. Small x is the integrand. Okay. This is X dpx. Okay. Integral. You are integrating with respect to this spectral measure. I mean, I will tell you what it means. This means the following. Some xi in H, okay, for some xi in H, let xi be in H, okay. Then xi is, I mean, this X is an unbounded operator, okay. I'm just recalling what we did, okay. Then xi is in domain of X. If okay, well, before that I have to define some other, sorry. So you have a spectral measure. P is a measure. I mean, P is a function from the Borel sigma algebra taking values, and it's there, that's hiding there. Yeah, it's taking values in projections. Okay. Now, if you evaluate through inner product, you get a complex measure. Okay. So given xi and eta, and please don't, these things are not needed later. Okay. This is just to understand what is happening, how you get a distribution on the real line when you have a random variable. That's what I want to say. Okay. When you have a xi and eta, two vectors in this, then you can define P xi and eta for E is going to be the inner product. You take the xi and P of E eta. Okay. So P xi eta is a complex number. This is in complex number. So this is a complex measure. Okay. Okay. And if xi equal to eta, this will be a positive measure. Okay. That will be a positive measure. I mean, if you can take P xi, okay, is positive. Usual positive measure. In fact, it's a probability measure because P of the whole thing is 1. So it's a probability measure. Okay. So a xi in H, okay, that's xi in H. Then this xi is in the domain of H, X. Okay. If this integral x squared, this is a measure, ordinary measure. Okay. With respect to this measure, this is less than infinity. Then it is in the domain of X. Okay.
For the previous universal, if that xi is not probably
Xi should be normal. Otherwise, the measure always exists. Okay. It's a positive measure. Yeah. If it's a probability measure, if xi, norm xi is 1. Otherwise, the measure of the whole set is, yeah, correct. Okay. So this is, I mean, so this is less than infinity, then X is, then xi is in the domain of X. Okay. And further, what is this? You want to find what is X. Okay. So you want X is an unbounded operator. So how it acts on the domain you want to know. To how it, so you want to, how it acts on the domain means it will take something in the domain to some element in the Hilbert space. You want to know that element, that image. To know that image, it's enough to know it's the inner product with anything. If you know a vector, inner product of some vector with every element, then you know that vector. I mean, by definition. Okay. So that is what you want to know. So you have this xi, x eta. So this is what you have to know. To know x, this is what you have to know for all xi, and for all eta in the domain. Okay. So this is equal to integral x dp xi eta x. Okay. This is but this is integral with respect to complex measure, which you can define. Okay. In fact, any complex measure can be decomposed into real measures. Real measures can be decomposed into Pascal. All these things work well. Okay.
So psi need not be in the domain.
Xi need not be in the domain. For xi in H, okay, and eta. I mean, but it's enough for domain because domain is dense. If you know this for any xi in the domain, then by continuity, you know for everything. Okay? It's enough to know it for xi in the domain. Okay. It is not needed, but it's not needed to be in the domain. Xi and eta in domain of X. Okay. Okay. So this is what is spectral theorem. Okay. Now spectral theorem says that you have something, you have some real line where you can write the operator like this. Okay. So this is, I mean, this is what is X is a self-adjoint operator is called as a random variable or an observable. If you remember, you are not, you know, in his class, he said that an observable, we don't call it as an observable something, quantum, there's no contradiction about it. You don't call a quantum probability space, whatever, I mean, that's not observable. But here, when you have a single random variable, whatever single X, and you have a quantum state, then you get a distribution, which is a classical probability distribution. Okay? So we have an observable, the whole thing is classical. Unless you encounter two operators which don't commute with each other, the situation is classical only. I mean, we have only classical probability theory. Okay, there is no quantum probability or something. So even if you have some collection of operators which commutes among themselves, then you have only classical probability distribution. You will be working with L infinity or something. So it will be whole thing will be classical. So we are calling a single operator X as a self-adjoint operator as an observable or a random variable in this setup. Okay. So when you have the single operator, then you have a distribution on this. Okay. So if X is an observable, this is the definition. X is an observable or a random variable. Okay. Then there exists a distribution, there exists a probability measure, then there exists a probability measure on R, which is actually supported in the spectrum of X, but let us not worry about it, on R by the following. Mu of E is going to be observable random variable on a quantum probability space. I mean, we need a quantum probability space on a H and a rho. Okay, we have a Hilbert space and a state rho also. Okay, then mu of E is going to be rho of XE. That's all. Rho of rho of P of E, where P is the spectral measure corresponding to X. You have a self-adjoint operator X, then you have a spectral measure corresponding to that, which we call it as, maybe I will put a X on the top of it. Okay. I mean, there is a probability Px. Okay. We put X everywhere. Okay. So, I mean, please put X everywhere. Okay. So, corresponding, so we have a random variable X, then we have a spectral measure corresponding to that. Okay. Using that spectral measure, using this rho, you can get a probability measure mu on this, mu on the, because the whole, the row of, what did I write? Sorry, object. There should be trace. We have written row. I'm in the, my mind, I have the linear functional thing. So this should be rho P of E. Sorry. Rho is a trace class operator. No, this is the writer. I'm sorry. Okay. So let me say it again. Okay. This is for all E in the Borel sigma algebra R. So if we have a set in the sigma algebra R, Borel sigma algebra R, then the probability of E is going to be trace of rho. You take the spectral projection corresponding to it. So that is a spectral projection. So when you multiply a bounded operator by a trace class operator, it is a trace class operator. So the trace is finite number and it's a positive number. This is positive because the following, this is equal to trace of, this is positive, no, rho power half Pxe, then rho power half. You can write it like this. So this is positive. So this is positive number. Okay. And if P of the whole set is going to be 1, you can verify that this is a probability distribution. Okay, we have went through this in the last course. So this is how you get a probability distribution. Given a state and given a random variable through spectral theorem. I mean, in the finite dimensional, it is the spectral theorem it's just clear. It's very easy. Here you have to take the continuous probability space. Okay, you have to work on that. You get a spectral measure on that. This is how you get a spectral measure. Okay. What is the next one? Okay, so this is how we get a probability distribution. So shall I recall what is a symmetric Fock space for you? Huh? Okay. So this we can assume that we start now. Okay, we start here. I mean, the whole thing starts now. So if we have a Hilbert space, some Hilbert space, maybe I want to use H for a different thing. Let K be a Hilbert space. We will take finite dimensional Hilbert space. Okay, Hilbert space. Okay. Then you can define the tensor product K tensor n times. Okay. Okay, which we call it as K tensor n. K power n. So this is the n times tensor product. So if you have a permutation Sn, then you can define U sigma from this K tensor n to K tensor n. So what is K tensor n? K tensor n is you take the formal tensor, xi1 tensor, xi2 tensor, xi n, and you take the linear combination. You take the elementary tensor and you are taking the linear combination. Okay. Don't make the mistake that the elementary tensor is not a vector space. You have to take the linear combination. Okay. So then you have U sigma. U sigma defined on the elementary tensors acts like this. Xi1 tensor up to xi(n), okay, is equal to xi sigma inverse 1. I put sigma inverse so that we will get a representation. Okay, we need the inverse. So xi sigma inverse of n. You can define. This is the user. You can verify that these are all defined on your elementary tensor. You can verify easily that this preserves the inner product. Okay, so this extends to a unitary operator. So this is, you have to verify it. I mean, the nice thing about unitary operator is if you define on a set which spans the whole set, this is called total. If you have some subset, if you take the span and take the closure, and if it is everything, if it is dense, then that is called a total set. So if you have if an operator preserves the inner product on a total set, then it can be extended to the whole thing. Okay, that is a nice thing. This is not true about linear. I mean, if it is bounded on a total set, it need not be even bounded on a whole Hilbert space. But for a unitary, if it preserves the inner product on a dense in a total set, then it can be extended to unitary. So this you can easily see that this preserves the inner product. Okay, and it extends to a unitary on H. Okay, so this is U sigma, and the symmetric tensor product. And symmetric tensor product is all those xi in the tensor product n such that U xi equal to xi. All those elements which are fixed by this U sigma for all sigma in Sn on this permutation. Okay, I have written it correctly. Okay, all vectors in the tensor n tensor which are fixed by all this permutation action. This is what is called symmetric tensor. Okay. Now the Fock space, symmetric Fock space. I mean, I will not use the gamma. Gamma is this is for symmetric Fock space, but we are not going to use any other Fock space. Only symmetric Fock space we are going to use. Okay, the bosonic Fock space or the symmetric Fock space is this. Gamma of K is going to be C. The first one is C, then K, then symmetric tensor, 2 symmetric tensor, then K, 3 symmetric tensor, and like that. Okay. Direct sum. K, n symmetric tensor. Okay. This is symmetric tensor. This is infinite direct sum of all the symmetric tensor. This is what is called a symmetric Fock space. Okay. We will have a simple way of dealing with symmetric Fock space. This is this definition we may read anytime. As I said, we will be working with L2 Rn. Okay, we can define everything on L2 Rn in the finite case. When K is finite dimensional, we can do that. K is finite dimensional, but gamma of K is not finite dimensional, as you can see. K can be finite dimensional. All those K terms are N and the K symmetric terms are N. They are all finite dimensional. But since you are taking an infinite direction, it's not finite dimensional anymore. Okay. So, yeah. So what is next? So this is the symmetric. This is the symmetric Fock space. Okay. This is what is called symmetric Fock space of K. Now on the symmetric Fock space, there are some nice vectors. Define E of X. Okay. For X in K. For X in K, define E of X in the symmetric Fock space gamma of K by the following. E of X equal to, this is 1. 1 is the number 1 in C, okay, which is also called vacuum vector. Okay, the number 1. Direct sum X, direct sum tensor, 2 tensor, direct sum X, 3 tensor. I mean, so there is a 2 factorial, square root of 2 factorial, square root of 3 factorial. This is like exponential vector. There's n direct sum divided by square root of n factorial. Okay. So you take the infinite direct sum like this. Okay. This is what is called E of X. This is exponentiation of the vector X. Okay. Then this can be done for any vector in the ground Hilbert space. Then the inner product E of X, E of Y is going to be E power XY. We can verify this. Then this is true. And further, we have proved in the last course that this E of X, X in K, okay, this is something which is contained in gamma of K, is linearly independent and total set. That is, if you call E, this is not what is called E. The span is called E script E. Okay? That is span of E of X, X in K, and the closure, you take the closure in the norm, that is going to be gamma of K. So the exponential vectors are linearly independent and they are what is called, they are also total. Okay. Now, if you want to define an operator, you can define it on the exponential vector. And if it is nice enough, you can extend it to the whole space. Okay. So that is how the Weyl operators are defined. Now, if you have a, so now before that, let me show you what is, how to identify this. So gamma of Cn with L2 of Rn. So this is the identification. This was given in the exam. If you remember, gamma of C, we identify with L2 of R. This was a question in the exam. Okay, so I don't know how many people did that. Okay, I don't. You did that, no? I think so. Okay. Huh? You didn't do. Okay. So it's very easy. I mean, there is actually there was a mistake in the question. I didn't realize. I realized it later when there was in the second part. Okay, I didn't realize it. I mean, no, I should have put a U star conjugate, which I didn't do. That's all. There was no other mistake. I mean, but it's clear, so that's why I didn't strike my mind. Okay, so okay, so how do you want to identify L2 of Rn with this? Okay, so for us, H is equal to L2 of Rn. Okay. So in L2 of Rn, you define E of X for X in Rn. Okay, sorry, X in Cn. Maybe alpha in Cn. Okay. Okay. You have to define E of alpha. Maybe Z is better. Okay. Z in C. I think if he uses Z, KRP. Z. So E of, you define for Z in Cn, you define E of Z in L2 of Rn by, so this should be a function. Okay. Function which should be square integrable. E of Z acting on some X for X in Rn, of course. Okay. You should say how it acts, the function acts on this. So this is equal to, see, okay, I will come to that later. But this detail, if you understand, it's fine. Otherwise, it's not a big deal. Okay. So the E of Zx, this is concretely, we can write it like this. So this is not square root, power 1 by 4. Power 1 by 4. See, what is happening is there is this density for normal. I have to take the square root of the density. I will tell you why. Okay, so 1 by 2 power 4, then this exponential function. I mean, it will Ez acting on x is this. Okay, this is, I will write it in a small. By E of Z acting on x is equal to 1 by 2 pi power 1 by 4 into exponential minus summation. Then you have to take the inner product. Z is tuple, n tuple, right? Z is in Cn. Okay, Z1, Z2, Zn. So Zj xj minus summation Zj square minus, so here there is an half, here there is an 1 by 4 summation xj square. Okay, I think I have written it correctly. This is our exponential vector. Exponential vector is a function in L2 of R. Okay, so you can verify that this is square integrable. You try to integrate it. I mean, you have to use the fact that e power minus norm x square. That's what you have to worry about. All the other things you can shift it. Okay. Okay. So this is in L2 of Rn. Okay. Okay. I will give this as an assignment. Whoever is going to take credit, take it for credit. That, but you have already done means you don't have to do. So the okay. So this is a function. Then E of Z, if you take the inner product, E of Z prime, okay, that is going to be E of Z prime, right? Okay. You can take E of Z, you have Z prime, you know the integral, you have to take the integral, okay, integral in Rn, then you will get that is equal to this. So this will imply that there exists a unitary operator from L2 of Rn, okay, to gamma of Cn, okay, which takes this Ez, maybe you call it as E prime, I'm sorry, E prime Z or something, okay. No, let us call it Ez. I don't know. This function E of Z takes to the other E of Z, okay. If you don't mind, this E of Z is in L2 of Rn, which I am because I'm going to call both as E of Z. I mean, we are going to identify L2 of Rn with gamma of Cn. We are going to use the same notation for that, okay, wherever it lives. Okay, we are going to make this identification. E of Z going to this E of Z in this gamma of Cn. Gamma of Cn is a direct sum of symmetric tensor of Cn. There we have defined a E of x, which is an exponential vector. Here I am defining a E of x through this, E of Z through this. Okay. If we take this map, E of Z going to this E of Z, that preserves the inner product. And this is total here. So why is it total here? This E of Z is a total set here. I mean, this proof I said, this is total here because L2 of Rn functions with compact support is dense in L2 of Rn. Okay. So L2 of some compact, so you can approximate a function in L2 of Rn with a compactly supported function. So if you have a compact set, then L2 of that is the continuous functions are dense there in L2 norm. Okay. Now these continuous functions, this E of Z are dense there. I mean, span of this is dense there. You can use Stone-Weierstrass theorem, but they are dense in the uniform topology. Eh? Exactly, you have to use, yeah, right.
Yeah, okay. Yeah.
No, that will prove that these continuous functions, these functions, E of Z, they are dense in the L2 of, I mean, the continuous function on a compact set. Okay. But then uniform convergence will imply N2 convergence. So they are dense in L2 topology also, even though C of x is not complete. I mean, continuous function on a compact set is not complete with respect to L2 topology. They are dense there. So this implies that these things are, the span of these things are dense in the L2 of the compact set. But then you have already know that the compact set is dense. I mean, compactly supported functions are dense there. So because of all these things, these functions are total there. Okay. So I will leave it as an assignment to write all this detail that I mean, this is the assignment. Explicitly write the proof for this. This is isomorphic to this. Gamma of Cn. Okay. E of x is going to give all the argument.
Can you give the
Which idea? You have this exponential vector explicitly defined here. L2 of Rn, you have the explicitly defined exponential vectors. You have exponential vectors here. I mean, that is why I have written E of Z going to E of Z. Both are in different space. Okay. So you take this E of, maybe you use a different notation, but I am not going to use different notation. I might use gamma of, mostly I will use L2 of Rn for the Fock space. Sometime I use gamma of Cn for some reason. Okay. Then the exponential vector will refer there. Okay. That's all. Okay. So this E of Z, these exponential vectors are taken to that exponential vectors. Okay. And that preserves the inner product on a total set. But you have to prove that this is a total set. For that, you have to go through this argument. Sohn-Weierstrass theorem. When uniform convergence by dominated convergence theorem will imply uniform convergence will imply L2 convergence. So this is dense and compactly supported functions. Compactly supported functions are, I have given all the arguments. You just have to write it. Okay, that's all. Convince yourself. Okay, that's all. So L2 of Rn can be identified with gamma of Cn, or if you want, we can work with L2 of Rn itself. Okay, so on this we want to define the Weyl operators. Okay, which can we define in gamma of Cn? So Weyl operators. That's all we want to define. Okay. So what are Weyl operators? So what is happening is the following. So we want to define operators in L2 of Rn or gamma of. So we have H is equal to L2 of Rn, which is also same as we are identifying with the Fock space. Symmetric Fock space correspond to gamma of Cn. Okay. So if we have a vector Z in Cn, okay, we define W of Z, okay, acting on E of alpha, okay, where alpha is also in Cn, okay. Just by the usual way, you know how to write it. This is just norm Z square by 2 minus the inner product between Z alpha, E of alpha plus Z. Okay. I mean, it is just E of alpha going to E of alpha plus Z. But you need those scalars to make it unitary. Otherwise, it will not be unitary. Okay. So this preserves W of Z, preserves the inner product. You can verify. Then we have verified these things in the last course. Then W of Z, E of alpha, W of Z, E of beta, okay, is equal to E of alpha, E of beta. You can write it down, explicitly write it down. I mean, you can direct verification, okay? Do that and then it will follow that. This preserves the inner product on that. So this implies W of Z extends to a unitary. Unitary on this Fock space, okay, L2 of Rn. Okay. Here for that, we are using the property of gamma of Cn or whatever. I mean, we move here and there, okay? So we have verified it for gamma of Cn, so the same thing will work. Okay. So W of Z, these are all what are called Weyl operators. Okay. These W of Z are called Weyl operators. Weyl unitaries or Weyl unitaries or Weyl operators. Weyl operators. They satisfy what is called Weyl commutation relation. Satisfy that this is what is called canonical commutation relation or Weyl commutation relation, or this is the, I mean, there is another version using the position momentum operator, which we will get to that. Okay. So this is the Weyl form of the commutation relation. So, okay. CCR, canonical commutation relation. CCR. That is W of Z, W of Z prime is equal to e power, there is a minus, I believe, imaginary part of Z prime, W of Z plus Z prime. They satisfy this relation. This is what is called a projective representation. That is Z going to this W of Z This is what is called a projective representation. That is not a representation. This Cn is an abelian group. Okay. But then Z going to W of Z is not a representation of the abelian group. This is what is called a projective W of Z. If it's a representation, if W of Z times W of Z prime is equal to W of Z times Z plus Z prime. But it is some constant times is W of Z plus Z prime. So that is why it's called projective representation. Okay.
Is it like a representation in the projective space?
What is the
But
project?
projective space, W Z will be equal to all the multiples of W of Z.
Say it again. The projective space.
In the
What is?
projective space, you're like forgetting about scalar multiples, right? So is it a representation of the projective space? Is that all I'm asking? In the projective space.
In a sense, yeah. Let's talk about it later. Okay. So, this is and further we proved the following. We'll go through this proof again because in the last semester I gave a proof because there was no time, and the KRP's proof is through probability, which I didn't want to go through. And other proof is a bit longer, so I didn't go through it. But I gave a proof using unbounded operators, but there is not some clarity was not there. We'll either go through, if you some more than one person take it for credit, either you present it or I will present it later. Okay, we'll go through the proof again. Further, this is true. W of Z in Cn. Okay, this collection, this is irreducible, whatever it means. I will tell you what it means. Irreducible. This means the following. You take the algebra generated by W of Z. Okay, Z in Cn. Okay. This algebra is strongly dense in all operators, B of L2 of R. That is, you take, this is strong topology. I will tell you what it means. Strong topology is equal to all bounded operators on L2 of Rn. L2 of Rn, or which is gamma of Cn, B of gamma of Cn. Okay. This is what is called irreducible. This is equivalent to saying what? So what is strong topology? I said strong topology is point-wise convergence. Okay. This just means,
Irreducibility means like there's no invariant subspace.
it's exactly same. Okay. So this is an irreducible one factor. Then this is equivalent to saying this W of Z in Cn. You take it and take the commutant. All operators commuting with this. That is just scalars. Okay. That tell you that there is no invariant subspace. This is equivalent to this. This is because of what is called double commutant theorem, which we proved last time. So shall I tell you what is double commutant theorem? It's needed. See, there is something called von Neumann algebra. See, we have strong topology. See, you have B of H is all operators, bounded operators on H. Okay. Then we say that, so usually there is a norm topology. There is a norm on this. You can talk about norm topology. But norm topology is not useful most of the time. So we use this following topology. For all Xi in H. If something converges for all Xi in H, then we call it as this is what is called strong topology. Okay. There is a theorem of von Neumann, which says the double commutant theorem, which says that, so if you have a subspace M contained in U of H, okay, is strongly closed. It is closed in the strong topology. Okay. Closed. Actually, you can use other topologies also, but I don't want to bring in all those topologies. Sigma weak topology, sigma weak topology. It's the same thing, except norm topology. For an algebra, the closure is same if you take in any of these topologies. Okay, but let us not talk about those things. This is equivalent to saying M is equal to M double commutant. By commutant means you take M commutant is equal to all those operators T in B of H, okay, such that Tm equal to Mt for all M in M. If we have a M, which is an algebra, then commutant is all operators with commutes with all of M. Double commutant is the commutant of the commutant. Okay. So if M is equal to its double commutant, that is equivalent to saying the M is strongly closed. Okay. So if M is B of H, That means it is equal to its double commutant. So its commutant should be C. Right? Or this strong closure of this is B of H. That means its commutant should be just C. I'm saying that here, I'm saying the Weyl operators, you take the algebra generated by the Weyl operators. What is the algebra generated by? You have to take all sorts of products, all sorts of sum. Okay. Then you take the closure in the strong topology. But the point is, if you take all sorts of product, that is going to be scalar multiple of the Weyl operators. Right? Because Weyl, you have this Weyl relation. W of Z is equal to some scalar times W of Z plus Z prime. Because of this, if you add any two operators, you take any kind of sum of Weyl operators, that is going to be again a Weyl operator, some scalar multiple. So the algebra generated by Weyl operator is just the linear span of Weyl operators. Okay. Now you have to take this strong closure. Okay. So any operator which can be approximated by linear combination of Weyl operators. That is what the algebraic strong closure of that. Okay. That is B of everything. But that is equivalent to saying the commutant of this. I mean, the commutant of bigger algebra is also same as the commutant of the dense subspace, commutant of something generating that. Okay. So the commutant of W of Z is just scalars, which is equal to that, which is the same. So these two statements are same. Okay. So we will be using this. This is an important statement. I mean, as I said, all those spectral theorem, all those things, mostly we will not be using. So just for clarity, you will need it, but in the computation we will not need it. But this is an important fact we will be using. Okay, that this is this Weyl operators. We will be using Weyl operators because everything we are going to define through Weyl operators. Okay, so Weyl operators are important, and Weyl operators are irreducible. That's also important. Okay, then finally, this is something I should have proved in the last semester. We didn't have time. This is what is called Stone-von Neumann theorem. I will state this, but the proof either I will prove or I will ask you to present. Okay, so this is Stone-von Neumann theorem. So the theorem is following. So let K be any Hilbert space. Okay, and yeah, and from alpha in Cn, okay, alpha to U alpha. Okay, so this is in B of K is unitary, is a unitary projective unitary representation. Is a projective unitary representation. Okay. Suppose if I have a projective unitary representation, okay, that means U of alpha times U of alpha prime should be scalar times that, but I'm going to write it. So we don't need the definition of projective unitary representation, satisfying the following. Satisfying the Weyl commutation relation. See, I'm just proving that the Stone-von Neumann theorem says that the Weyl representation, whatever, okay, any representation which satisfies the Weyl commutation relation is unique up to unitary. That's what it says. Okay. Any representation which satisfies the Weyl commutation relation, which is here, where is it? The yeah, W of where is it? Yeah, it's here now. Yeah, this is Weyl commutation relation. Okay, is unique up to unitary. I am going to state this. Okay. Okay. So satisfying U of alpha times U of alpha prime equal to e power I imaginary part. This is imaginary part of alpha prime times U of alpha plus alpha prime. Okay. If you have a projective unitary representation, I mean, this says it's a projective unitary representation. You don't need to define it again. Okay. It's a projective unitary representation. Okay. I should say that it's a strongly continuous. Is a strongly continuous. It should be continuous also. Okay. It's clear what I have written. Strongly continuous. Okay. Strongly continuous projective unitary representation. That is alpha going to the alpha going to U alpha should be strongly continuous. alpha is in Cn, so there is a topology in Cn. Q alpha is in somewhere, there is a strong topology. Okay.
Unitary representation means
No, this is Weyl commutation relation, but this implies it's projective unitary. Projective means U alpha times U alpha prime equal to some scalar times U alpha plus alpha prime. Representation means U alpha times U alpha prime equal to U alpha plus U alpha prime. That is representation. Scalar times that is what is called projective unitary representation. This, of course, implies that it's a projective unitary representation. Okay, scalar times. Okay, so if you have a strongly continuous projective unitary representation satisfying this Weyl relation, okay, then there exists a unitary W from L2 of Rn. There exists a unitary and a space, some other space, and a Hilbert space. It could be a small Hilbert space, K. Okay, there exists a unitary W, okay, where W is from L2 of Rn, tensor small k, okay, to K. Okay, such that W of maybe I use V, sorry, I will change to V because there is U already there, so I changed to W, but W is coming here. So again, so V, it's a V unitary operator V. V yeah, W of alpha tensor 1 V star. So V star is here, W of alpha is correctly written, is equal to U alpha. Okay. This is V. Okay.
go to bounded operators.
Yeah. So it's correct, no? V star will bring it here, W of alpha tensor. Then V, it should come to V. Correct.
Okay.
Correct. I have written. So it's correct. Actually, in the KRP's paper, it's written the V is from K to here. So small mistake is there. That's what I realized. So I wrote it correctly. The direction is, I mean, it's just a silly mistake. So it's written in the wrong way. Okay. So if you have any, so what it says is the following: if you have any unitary representation, collection of unitaries, which satisfies the Weyl relation, okay, then it will be like this. It will be like Weyl operator tensor 1. But then if you can see, if it is irreducible, it should be Weyl operator. Here, you see here, what is the algebra generated by this W of alpha? That will be B of the L2 of Rn tensor 1 here. Okay, tensor C or whatever. Usually we put 1 there. Okay. So, but if it is irreducible, then that K will be just C. There is no K. Okay. So this is what is called Stone-Von theorem. Which this is only true when the Hilbert space is finite dimensional. This is for Cn. In infinite dimensional, this is not true. Okay, so there will be still all the representation of an infinite, all the Weyl representation of an infinite dimensional Hilbert space is not known. It's still coming out. Okay, because mostly from physics people. So there are many representations. They are not classified. But in finite dimensional, they are all unitarily equivalent, provided they are irreducible. They are just determined by the number n, Cn. Okay, they are just, there is one, or it can be an amplification of that by some k. That's what this is. Okay, shall I take 5 more minutes? So this is Stone-Von theorem. I thought I will, but we took a lot of time on fixing this. So I wanted to do this, define this quantum characteristic function. Okay, I will just define that and then stop. Before that, let me say, this is again recalling what we have done. Okay, so if we have an alpha in Cn, okay, so let us finish. Then we have W of alpha, which is a unitary in B of L2 of Rn, okay, which is a Weyl operator, W of alpha. Then if you take W of T alpha, this is a unitary group. It's a group of unitaries. Unitary group. If T is varying. Okay? Because there is W of T alpha times W of S alpha is going to be W of S plus T alpha, because there is no imaginary part between them. So it satisfies this Weyl relation because the imaginary part is 0 between T alpha and S alpha. Okay, so it's going to be a unitary group. Okay, so it will be a group. So Stone's theorem, there is something called Stone's theorem, says that there exists an unbounded self-adjoint operator. There exists an unbounded self-adjoint operator P alpha such that this W of T alpha should be equal to e power minus I T P alpha. I mean, this e power I T minus, so you have to make sense of this, but this can be made sense using the spectral theorem if you want. But you can just remember this form. I mean, it's not needed. I mean, in the sense that we will not be explicitly using this anywhere, but it is better to know this, because that is how we get the characteristic function. If you want to understand why it's called characteristic function, it's better to know this. Okay, so that is why this you can actually so how is this e power it alpha? This is through spectral theorem. What is W of T alpha? W of T alpha is integral e power itx dpx. So the P is the spectral measure. It is defined like this, right? Okay. This is what this is, where P is the spectral measure. P is the spectral measure of X. P alpha, sorry. There is an unbounded operator, so it has a spectral measure corresponding to that. Okay. And if you integrate e power minus itx with respect to the spectral measure, you get W of T alpha. That's what this is. Okay. So that P alpha is what is called Stone's generator of this. T alpha is what is called, I should use capital letter, Stone's generator of W of T alpha. Okay. This unitary group as a generator, and that is this P alpha. Okay. So now with this understanding, we can define what is called quantum characteristic function. See, usually what is a characteristic function? If mu is a measure on something, on Rn, okay. I will erase this, write it and erase this. Mu, a measure on Rn. Okay. Then you have this mu hat, which is defined on some x in Rn and x in Rn. Okay. Then this is defined as e power minus itx or itx, minus itx. Okay. Some people write itx, it doesn't matter. Then you have to change everywhere. That's all. E power itx d mu x. This is integrable because that has norm 1, mod 1. So this is integrable over Rn. So if mu is a measure on Rn, this is mu hat x is defined by this. This is what is called a characteristic function, or a Fourier transform of this measure. Okay. Then this characteristic function uniquely determines the mu. And Bachner's theorem says that if you have any function which satisfies some condition like mu hat of 0 equal to 1, okay, and mu hat is some function, sorry. If you have any f function, Bachner's theorem, I will erase this anyway. Bachner's theorem says the following: if f of some function f of 0 equal to 1 and f is continuous and f is positive definite, I will recall what is positive definite. Okay, f is positive definite, then it is a characteristic function of a measure. Okay, so we want to get a corresponding theorem in the quantum case. Okay, then we will work with just characteristic function to prove all that. Okay, so that is the aim. So positive definite. Okay, a function. So if you have a function f from Rn to Rn, if on any set. Okay, so let me see. So there are two ways of saying a function. Usually positive definite is if you have any set, yes. No, not integration. This is a different thing. If you have a function, k is a function from C, S cross S to C. Maybe I will add it as a definition. Okay, definition. Is positive definite. If this forms a k xi, xj, okay, for this ij, whatever, is a positive definite matrix for all x1 up to xn. Okay, for all contained in this is set. You take any set, possibly maybe you repeat it, doesn't matter. Okay, you can repeat also. I mean, so that the subset does not actually, this notation does not make sense, but you have to, I mean, you can repeat x1 up to xn. So you take something and something in S, okay, then this form, this is a positive definite matrix, or this is also equivalent to saying summation Ci, Cj, Cj, maybe I put here because with respect to our inner product being here, Cj, Ci, Cj, Cj bar, k of xi, xj is positive. Yeah, for k of xi, xj is positive for all C1 up to Cn. This is contained in Cn. This is contained in C, and x1 up to xn in S. Okay. This is the definition of positive definiteness. A function is positive definite if you have a single function from Rn. So if yeah, you can use S. No, you can't use S. You need something. You have to subtract, no? So a function is positive definite. If f of the corresponding function, I mean, you just have to, I mean, f of you two variable function s minus t you have to take. That's all. That is if you, it is summation ci bar cj f of xj minus xi is positive definite. Okay. For all C1 up to Cn, x1 up to xn. If you don't mind, I will define quantum quantum characteristic function, or I will do it in next class. Maybe I'll recall and do it next class. What do you prefer? Okay. Anyway, I will not be able to give a proof today. So, anyway, so since it is curious, so if you have, if rho is, so H is a, I mean, this is specific for bosonic symmetric Fock space, this definition. This is not for general H in general state, okay? Because we are defining it through the generator, Stone's generator, okay? So H is equal to L2 of Rn, and rho is any state on that, rho, any state, okay? Then rho hat of any Z, where Z is in Cn, okay, is equal to nothing but trace of rho W of Z. That's all. Okay, this is for all Z in Cn. This is what is called quantum characteristic function. Okay, this rho hat is called, why it is called quantum characteristic function? Why it's called a quantum characteristic function? Because if you just fix Z, okay, fix Z in Cn and T in R, okay, then you define phi of T equal to rho hat of Tz. Okay, this is just the characteristic function of the distribution of this, I mean, this P of Z. P of Z is a generator of W of Z, which is a random variable, which is a self-adjoint operator. And rho generates a distribution on the spectrum of this. And it is precisely the characteristic function of that distribution, probability distribution. Okay. If you fix a T, if you fix a Z and use this. So that is the probability distribution on the real line. So it's a one variable. I mean, it's a function of one variable, phi of T. Okay. So this is precisely that. So, but if we want to include all sorts of distribution, so we have to use the quantum model. So if you fix any Z and use a Tz, then you get a single characteristic function. Okay. So if you vary Z and you get a quantum characteristic function. That's what happens in quantum probability always. If you have a state, if you fix some whatever you call measurement or something, no. If you can't, you call you say even in 2 dimension, you have a state. If you fix two bases, two coordinate, I mean, two orthogonal projections or something, Then you get a distribution. You get a distribution on 2 point. Yeah. But you can change the basis, you get distribution, some other distribution. So if you change the projection or whatever you want to measure, okay, you change it or you change the random variable. See, he defined the, if you remember, he defined some, if you take projection, for example, you take the value, see, your measurement is actually in this thing given by something like this, 1 up to k. And suppose let us take projections, P1 up to Pk. Then the random variable is k times Pk. It is precisely the meaning here, whatever precisely I have written is Pk times Pk. You are measuring this random variable. So you will get a distribution on this 1 up to k if you use this. Okay. So, but we are doing in a continuous way. And this is precisely this P of, this is the distribution of P of Z. Okay.
So like traces your integral.
Yes, trace is like, yeah. It is integration.
Yeah.
If you take the trace, if you take the, with respect to, if you fix it, it will be just the integration there. Right? Yeah, trace is the quantum analog of integration. Right. Okay. Correct. Expectation. Right. Okay. So let's stop here.